computer. Welcome back, everybody. And so I have the first thing I want to do is do my administration stuff for this week. We don't have that much in this class, but I wanted to do it anyway. I have, number one, I've started posting the links to our Zoom classes. Each week I will post them as an announcement on Canvas, because some people aren't getting the emails or they're getting them late, and so I'm posting them there at the beginning of each week. So if you can't find it in your email, go to Canvas and it should be there under announcements. Okay, and in fact, when you hit your when you go to your dashboard page, you should actually see the little announcement thing light up, and you can just click on it. It'll take you right there. Okay, so that's going to help some of us who are having issues. So we have, let's see, we're going to continue on with fragmentation and a fragmentation exercise today. And then we're going to have kind of a home, we're going to do a strategy session on Thursday. I'm going to give you some problems and we're going to work through them. It's a group activity. So I'm going to send that out hopefully today or tomorrow so that you have an opportunity to either print it or we can actually, you just have to write out the answers before you upload it to Canvas for a final part. But again, this activity is something we're going to sit there and work together. I'm going to kind of mute myself a little bit and let you guys talk through things. And, you know, like, well, what fragments could be possible? What are this? What's the math? You know, and we're going to work through several problems that way on Thursday. And so that'll be our first group activity. And then that'll close out all of Mass Spec. And we'll begin with our next week. Okay? So I'm going to go ahead and go to that. There we go. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's right. Okay. All right. So now what I'd like to do is I'd like to go ahead and share my screen. I want to go over and the 9 rules of fragmentation, and I want to show you examples of each of those 9 rules. And then I have today, we're going to just work one thing at a time, one thing at a time. Can we mute a microphone here? Let's see. I'm going to mute your microphone there because we have some background noise. But okay, so let me go ahead and share my screen and go over. The first thing I want to go over is the last few questions on the problem set we looked at last time. I'm going to answer those questions, and so we have that problem set from last time. I'll do 6, 7, and 8, or the last 3, and then I'll go through the fragmentation, and then we'll have an exercise. Okay. Again, if you have a question, I have the Zoom chat. We're a small enough class. You can unmute if you need to, and we can talk through this. So, all right, I'm going to go share my screen. Let's see, where did it go? There it is. All right. So this is that problem set we were working on last time, and we were trying to use the process of elimination to help us figure out which one of these compounds was that. So now we have 2 choices. We have 2 compounds and 2 mass spectra that we can play with. And so what we're looking for in this is favored fragmentations versus unfavored fragmentations. Okay, so in the case of our 2 structures here, we have a bromine on both species. One of the bromines is really susceptible to SN2 or elimination to give us a secondary carbocation, and one is on the benzene ring. And so if it eliminates, it has to eliminate through a radical fragmentation. So let's look at that a little bit. And so in the first spectrum we have here, where'd my pen go? Oh, there it is. I'll put my stylus in my pocket for some reason. In this first one we have here, I'm going to do the first one in blue so that we can start figuring things out. We see this number peak here. So right away we're thinking bromine, okay? So we have bromine and we lose a fragment and we still have bromine. Okay, so that means we've lost mass and still have a fragment here. And the mass loss is from about 200 to about 170. So that's a mass loss of about 30. Okay, So what fragment is a mass loss of about 30? So we go to our table here, and that's about, let's see, a C2H5 maybe, a C2N. We don't have any nitrogen, so it can't be any of those. So it looks like maybe a C2H5 was a fragment loss. So that makes a little bit of sense there. Because remember, we have benzene rings here. And one of our rules in fragmentation is that when you have a benzene ring, it's going to give you the benzylic substitution, meaning it's going to clip here or it's going to clip here, okay? So remember, because when we have that benzene ring, the benzylic carbon is really, really a good stable fragment, and we end up getting the fragment of 91, or that tryptolium ion as a fragment. So that happens in all benzene rings with an alkyl chain on it, okay? So if we think of that as our first fragmentation possible, then we have a total of 30 right here, and a fragment is the C2H5 is 29, okay? So that might be exactly 29, but it's around 30, just to tell us that. So we have a possibility of a C2H5 fragment coming off. Now, right away, if we look at this compound, on here, it would be very difficult for us to get a C2H5 fragment off there, because if we fragmented here, we would have a C2 and a bromine fragment coming off. So that'd be a much heavier fragment, right? And the fact that the bromine would probably fragment off first, giving us a different thing. So maybe, okay. So we understand why we're getting this first fragmentation, and the bromine would still be on the major fragment, possibly. Okay. Now let's go look for evidence in the other spectrum. Okay. So in the other spectrum here, we see that we have a bromine in our parent ion peak, and our base peak, our biggest peak here, is a 91, okay? So that's suggesting that it's clipping everything off and giving us that base peak, okay? So our next fragment, though, is this 120. What's 120? If we look at our thing here, it's a benzene ring of some sort like that. But remember, our bromine is 79 and 81. So if we took 120 away from that, we would have, let's see, let's just take it to 80, that would make a fragment of 40. So a fragment of 40, if we look at our table, is a C3H5. Ooh, let's go look at our structure again. Okay, so we have a C3H5 if we take the bromine off. So we have a C3H5 with a bromine. That correlates to this peak. So that entire fragment is coming off with the bromine to give us this peak. Okay. So do we think that, what other piece of evidence do we have here? Let's see, we still have a 91 here, so that could be either one. We don't have a real big peak here. I think these three major fragment peaks here suggest that we had bromine on there and we lost a fragment, this fragment here, C2H5, and then that gave us our 91 peak, and then we have bromine as our last peak here. So the evidence suggests that this is this fragment here, and that having this bromine side chain clip off to give us that 120 gives us this spectrum there, okay? So the evidence suggests that because of this 120 peak here, we've actually clipped this entire thing off. When we look at the lost peak here, we're clipping something off, but we still have bromine on the fragment. So I think this gives us enough evidence to suggest that these are now properly assigned, okay? You know, and that's one of the things about, you know, by looking at thousands and thousands of these things, you'll see the rules happen over and over again. And so by just practicing looking at your fragments and getting the best guess based on the fragments you see. And if you see a fragment that is a weird one, that is like, well, how would he ever get that fragment? Well, maybe that's not a primary fragment. So we want to look at like the biggest ones, the top 3 biggest ones, and then see if we can't rationalize an answer from that first. Okay. Any questions about that? Okay. We're going to go through several more of these and do more of these, but if you have questions, please ask. Okay. So now we had, in the next one, we gave you 3 isomers, constitutional isomers of compounds. So they're basically all the same mass, okay? And we're asking you to pick the corresponding one based on what we see, okay? So if we look at it structurally, this compound here has a benzylic carbon. This structure here has a benzylic carbon. This has a carbonyl, which will not give us that benzylic fragment because of one of our rules, which is that fragmentation with the heteroatom. It's going to want to have the charge leave with the heteroatom and cleave in that position. So these 2 spectrum right here, I mean, these 2 compounds right here should have a 91 as a fragment here, and this should not have that 91 as a fragment. So let's look at that first. And so here we have a good 91 peak, which is what we're expecting. And in this one, we also have a 91 peak, but in this one, it's completely missing, okay? So right away, we have to look for the one that doesn't have that benzylic carbon with hydrogens on it to give us that benzylic fragment. And we only have one compound that does that, which means that this compound with the ketone here is this middle spectrum here, all right? So we just assign this as the number 2 spectrum, okay? So, great, now we just have to figure out the other 2, okay? So let's think about how this would fragment now. I'm going to erase my red marks for everything but the one we have here answered. And now that we know we saw our 91, so we know that those are there. I'm going to switch over to blue, and I'm going to think about this one right here. Let's think about what fragments we should see in this. So we should see a cleavage. If we cleaves here, we should get that 91 benzylic peak we're looking for. But what's the mass of that other peak, right? We have a carbonyl and a methyl group here. And if we look at our table, that's a pretty common fragment of, let's see, where is it? It's a methyl group with a ketone. A methyl ketone fragment is, gosh. Oh, it's 44. 44 is a methyl ketone fragment. So we have CH3, and so that's a 44 peak right there. So those would be the 2 major fragments we'd expect from this one right here. Okay. Now, if we were to do this one right here, we would actually see the benzylic cleavage here as well. So it should also give us a 44 peak. So let's look for 44 peaks in both of these spectrum here. Okay. So in this one, it's not really very big here. But in this one, we have a very strong 44 peak here. Okay. So we have our 91 and we have our 44 on that one. All right. So how can we differentiate that? Okay. So now let's look at our 2 compounds here. So if this is our major fragment, the only other fragment would be this, which would give us a methyl group. And we really don't see anything in the methyl region there and the methyl region there. Okay. And we have our 91 peak here. Okay. So let's think about how else we could fragment this. Okay. Remember, one of our rules of fragmentation is if you can lose a small molecule like CO. That's one of those favored things. In addition to that, cleavage allylic to a heteroatom is also very common. So what if instead we fragmented this? I'm going to change colors again. So let's see what evidence we have to support this one right here. Okay. And so what we're expecting to see is our 91 for this, and then because of the cleavage here, this would give us a 44. But what would a fragment cleaved right here give us? An oxygen, a carbon, and a hydrogen should give us, let's see, 16 plus 12 plus 1 is 28, 29, right there. So let's look for the loss of 28, 29 somewhere here. So we have 91, and so that's maybe there. So this is our mass peak here. So what would be the loss from here to, okay, that's going to be the 44. All right, let's look at this one here. That's our only loss is a 44 and then the 91. So we have a much more complex pattern here. So one of these losses here, okay, well, here's our 29 peak here. Do we see that loss of 29? Is this a loss of 29 right here? That's 31. Oh, that is a loss of 29 or 30 right here. Then this would be another loss. This is 91 and this is 104. So that would be a loss of 12 or 13. So that'd be a CH2 or a CH group loss right here, this 12 or 13. So we have the loss of COH and then the loss of CH2 to give us our benzylic 91 peak. Okay. So that's suggesting we're clipping it here first. We're doing this clip of getting this thing off. Then we're clipping it here again to get our 91. So see how the fragmentation pattern on this is more complex because you can lose CO, which is a small molecule. You can lose hydrogen. You can lose a CH2 to get to your primary peak, our base peak, which is the 91, the benzylic cation. So that suggests, oh, my thing says internet unstable. Let me switch over to the right one. Yeah. I'm switching over to my other Wi-Fi network. All right, yeah, there we go. That's a little more stable. Okay, so that suggests that we can lose smaller molecules that are, so we see a more complex fragmentation pattern if our heteroatom is toward the end of a chain. So I suggest that this one right here is our number 1, and this right here is our number 3, is the compound up here with the benzylic ketone. Okay. Okay, so again, we're doing evidence-based. We're kind of taking our best guess with the evidence we're given. Okay. Are these absolute? No, we have a good argument for each of these things. And actually, when you actually take the materials and run each of them separately, knowing which one is which, you can verify that those are actually all 3 correctly assigned. All right, now we're going to take a different approach on this last one. We have 3 isomers of the alcohols, and we're going to use a couple different fragmentation rules to help us assign this. Now, one of the things we're going to see is that long chains, that are long straight chains, start clipping off at the end. And so you see, 14, 14, 14, 14, 14 losses, okay? So we want to look for that in our long chain hydrocarbon. Now, the other one we have is we know that we want to do this allylic cleavage near heteroatoms, right? So we want to look at which fragments would be generated from the different fragmentations next to that and look at which fragments are available to us. And then we need to start assigning things, okay? So let's start with this one right here. It's the longest, straightest chain. Therefore, it's going to do that thing where it's clip, 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 where we're just going to start clipping from the end as part of our fragments. And then the other thing would be to clip here to lose this allylic, this small molecule right here, or we can even see it lose water. It's not as favored to lose water because that gives us a primary carbocation here. So I expect this one to have that thing where it's where we just have equal clips as we go down. Okay. So now let's predict some fragments we'd see here. So one good fragment we'd see here would be maybe that. So we'd have a C3H5, and C3H5 is one of our, is it a 40? It's not 45, it's C3H5 is a common one, and it is 41. So we would get a 41 fragment here, and we'd have a C2O, which is, let's see, that's a fragment, which is also 44. So that side would be 44. But we also have the option of fragmenting here, giving us a long chain. So we have maybe some equal size fragments here. All right, so let's look at the last one. I'm going to change inks again here. So if we do this cleavage-wise, we're going to cleave allylically, so we're going to cleave here. And so we're going to have a C2H5 chain, which is smaller, right? It's only 24 plus 5, which is like a 29 fragment. And the other fragment is a C3OH. So that's a larger fragment. That's bigger than the 44. If we look at our table, so we don't have to memorize everything, a C3O peak should start up around 59. Where is it? Yeah, there it is, 59. So that side would give us a 59 peak. And if we clipped it the other way, it gives us the same two fragments, just in the opposite sides. Okay, so just by looking at these, where the location of the OH is, we can kind of get an idea of what we expect the spectrum to look like. Okay, so now let's look at the three choices we have right here. And those three choices we have this one right here. It kind of looks like that clip, 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 clip kind of thing we're looking for. Let's look at this one right here. On this middle one here, we have a 59 peak, and it looks like a 31 peak right here. And on this one right here, it looks like a 44 peak, and then there's also maybe a 41 in here somewhere as our major peak. Okay, so just assigning those base peaks, let's look at what our predictions were. Okay, we predicted this first one to be that clip, clip, clip. So we think that's probably the last spectrum because it most fits that long chain hydrocarbon pattern. Now let's differentiate between the next two. This one had a predicted 41 and 44. And if we look at this, the second one doesn't have it has a 41, but it doesn't have much of a 44, but this is its major peak here. So I think this 2-propanol would give us that as our major fragment. Remember, we didn't predict 59 as a major fragment on this one here, but we did predict a 59 as a major fragment on this one here. So the 3-propanol is the middle spectra, the 2-propanol is the top spectra, and the 1-propanol is the bottom one. Okay. Do you see how we're using our predicted evidence, and then we're looking for evidence, and then once things are not exactly right, we're looking for additional pieces of information to match. Okay? All right, questions on that. So that was the homework set. Okay. And what I want to do is I want to go through those same 9 fragmentation rules, and I want to show you patterns. I didn't show you patterns for all of them last time, but I found a good pattern for this one. Where'd my... Oh, there we go. Okay, so I have a rule, and I actually have uploaded these to tracks under the, Canvas under the file side. It's called MS Fragmentation and Rules, okay? So what I have here is a series of spectrum and the rules that we have. Okay, so this first one is actually an example of Rule 1 and Rule 3. So Rule 1 is that a straight chain hydrocarbon tends to have a higher molecular ion peak than a branched hydrocarbon. okay? And it does that, and it has a typical clip, 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 clip pattern of chopping off 14, 14, 15, 14, 14, something like that. So in our number one example right here, the first part of it is we see a straight chain hydrocarbon, and it actually has a fairly, noticeable molecular ion peak, okay? If we take it's the same molecular weight, however, it's branched now. And so by the branching, it tells us that, number one, it's not going to have a very favorable molecular ion peak because the branching encourages that tertiary carbocation fragmentation. And so we're going to see clipping of here and clipping of here, okay? So we're going to see fragments that are associated with that as our primary and base peak. So that's actually rule 3. The more substitutions you have where you can get tertiary carbocations or secondary carbocations, the more they're going to fragment. And what we see in this one, even though it's the same molecular weight, we have almost nothing in this upper range, and this major fragment is that clipping of those 4 carbons off to give us that tertiary carbocation. So that embodies rules 1 and 3. Okay, so let's go to rule 2. Rule 2 is the relative height of the molecular ion peak decreases with increasing molecular weight, okay? So even if things have the exact same functional group, the higher the molecular weight, the less likely it is to get all the way through the detector at the end without further fragmentation, and therefore that molecular ion peak decreases. So in this case, we have 2 aldehydes here. One's a long chain aldehyde, one's a short chain aldehyde, and this is our molecular ion peak for that, and it's fairly substantial, okay? It's almost as high as our base peak here. However, by having this long chain making it much, much heavier, we see almost no molecular ion peak associated with that. But we do see our fragmentations of this fragment coming off, and then this is that fragment here. So again, this also embodies a little bit of the heteroatom cleavage one, where you're thinking this is going to be a major cleavage point, giving us those 2 major fragments. But rule 2 is molecular ion peak usually decreases with increasing molecular weight. Okay. So I already told us about rule number 3, which was if it has branching, it will give us our tertiary carbocations, and that's why we'll see very few of the molecular ion peaks and a lot of these large fragments. Rule 4 is that benzene rings, saturated rings, and alkenes tend to, or things with double bonds and triple bonds, tend to give us a very prominent molecular ion peak. So in the case of benzene here, we have 2 peaks here. The 92 is actually just the ion peak, and then the 91 is having it lost a hydrogen to give it the benzylic ion peak. Okay, so you have your actual, your entire toluene ion peak is the 92, and that benzylic ion peak is the 91. Okay, and that's the major fragment, because remember, rings are pretty stable, so we see very little of the other ones because they're not as stable. The rings are so stable that they rarely break into other things. Now, that rings are stable thing works also with saturated hydrocarbons, okay? So in the case of aliphatic cycles like this cyclohexane here, we do see a strong molecular ion peak, stronger than you'd expect for something of this molecular weight. We would expect if it's a straight chain hydrocarbon, it'd be much smaller, okay? And then the fragmentations are going to be similar to breaking the chain across the middle and undergoing that kind of cleavage, homolytic and, I'm not homolytic, sorry, that kind of pattern cleavage, okay? Now, once we get to the alkenes, remember your alkenes can form your, stabilized allylic radicals and cations. And because allylic radicals and cations are particularly stable, we still see a significant ion peak, molecular ion peak. Okay. So what's that? Okay. So that brings us up to number 5. Number 5 is that double bonds favor allylic cleavage, okay? So think about allylic cleavage as the loss of 3 carbons, okay? So because it likes to stabilize that charge over the total of 3 atoms going back and forth, if we look at our resonance structure, it's going to want to clip here. Okay, so we see our major clip is going to be that first 3 atoms that come off, and that's going to give us a peak of 41. And then that remaining chain, the 1, 2, 3, 4, 5, actually gives us that other peak at 55. No, at 70. So because we want to clip off all 3 of these carbons together because of that stabilized allylic cation or anion or radical, we see that type of fragmentation pattern. Now, it's more pronounced when you have more than one, because now you have choices where you can get that cleavage to happen. And you would see fragmentation patterns like where this would be a good allylic position because it's allylic to 2 different. So this would be an allylic cation made from this side, and then this would be an allylic cation made from that side. So as you have these structures with more and more, you see that allylic cleavage happen even more spontaneously. All right, questions on that? So that's rule 5. You don't have to know the names of the rules, but it just helps to keep them in track here. So rule 6 says that saturated rings lose the entire alkyl side chain first. Okay, so in the case of the cyclohexane, it's going to clip the entire alkyl side chain off first. In the case of the cyclopropane, it's going to clip this entire alkyl side chain off, giving us our cyclopropane and this ethyl group as our major fragments. Okay. Now, this is slightly different from when we have benzene. Okay, so the key here is saturated rings lose the entire alkyl chain. Okay. Now, that brings us to the benzene. Now, the benzene loses all but the carbon next to the ring because it likes to form that benzylic ion. So instead of cleaving here like you do with a saturated system, because of the stability of the benzylic cation, we actually get cleavage here. Okay, so that's a subtle difference between rule 6 and rule 5, rule 6 and rule 7. Saturated breaks off the whole chain. Aromatics give us that benzylic cation, which gives us the tropylium cation, which is a nice big 91. Okay, so that's rule 7. Rule 8 is when we have heteroatoms, specifically oxygen and nitrogen in our system. It's telling us that it's going to fragment in a certain way to where it's going to fragment either next to, for example, here, or allylically here. It's going to be one of those 2 fragmentation patterns, and that heteroatom is going to leave with the charge, hopefully as a small molecule. It tries to leave as a small molecule. And so what we see here as a major fragment here is 30, which is a C3H, C3N. Oh gosh, I forgot it already. See, that's why we don't have to memorize this. We have a table. So that, yeah, C2N2 is that major fragment at 30. But over here, what we see is that we get this fragment that has 2 carbons and an oxygen in it, which is this 4143 peak. Okay. But the idea is that that heteroatom is going to be taking that charge with it in the fragmentation. Okay, and that brings us to our last rule. Okay, and this, think McLafferty rearrangement. Okay, if you have at least 2 carbons, and that the carbon, 2 carbons over from your carbonyl compound has a hydrogen on it, it can rearrange and transfer the hydrogen to our carbonyl oxygen, and then it extrudes out a small molecule of water. It'll do methane, ethane, water, CO2. Well, not these won't do CO2, but they'll do CO. So if the McLafferty arrangement, you see this nice big peak at 43 because it will kick out this fragment here, having transferred that hydrogen to the carbonyl. Okay. But in the case of this alcohol here, we're going to see a loss of 18 because it's trying to lose water. In fact, that loss of water, that loss of 18 happens so rapidly that we hardly see the molecular ion peak. So that'll happen a lot in these primary alcohols at the ends of change. All right, so those are a review and an example of each of these rules. Now, if you can go ahead and get out your predict a fragment, find a fragment, we're going to work through that now. Okay, and we're on schedule. All right. I'm going to take this moment to hopefully not cough. Okay, now that we have those fragmentation rules fresh in our heads, let's look at this particular compound and figure out what kind of fragments we expect to see. Okay, so one thing that we can see here is
43 peak.
Oh, question?
No.
Do you have a question?
No. Sorry.
Okay, there we go. Okay, so let's look at what kind of fragmentation we can get from here. So let's see, we want to do possibly this fragment here is a pretty common one, right? Because we have, that would be a C2H3O peak. That's a pretty good one because it is a one bond over from a double bond. So we might expect to see that as a fragment. And so that would be a C2OH5. And that would be, let's see, what kind of fragment would that be? That would be a 44. Just that would give us a 44 over here. And then we'd have the C3H7 and C3H7 is also a pretty common fragment we have at 43. Okay, so just that one cleavage at that one spot should give us those two fragments. Okay, so let's see where else it can. Let's take away that fragmentation spot now that we have those two fragments. And those two fragments would be the and the right there. So that's 44 and 43. Now let's see, what else can we do? Ooh, we actually have something that's long enough to do a McCafferty. So let's go ahead and erase those. If we redraw the structure here, take this methyl group and put it up here and put a hydrogen here, that means we can actually go ahead and do the McLafferty rearrangement. And so that would actually, this doesn't exist anymore. If we did that McLafferty rearrangement, trying to hide this right here. Okay, if we did that McLafferty rearrangement, we're going to end up transferring this hydrogen to here and cleaving here. Okay, so when we do that, we should get a OH fragment. Oh, there's no hydrogen there. And a 43 as well. So we get a 44 and a 43 as well, fragmenting the other way with a McLafferty. Okay. So the only other way we could fragment this would be to clip off the methyl group by itself. Gosh darn it. There we go. All right, clip it off right there. So we'd have a loss of methane, or CH3, which is 15, and then we'd have the remainder of the fragment here, which would be a C4 fragment, which is going to be something bigger than 57. It's kind of probably be higher, like maybe in the 60s. Okay. 1, 2, 3, 4 carbons at 12 each would be 48. Plus oxygen is 56. and hydrogen. So yeah, 59-ish maybe. Okay. Okay. So just looking at the ways we can fragment this, it gives us an idea of how we could have done this. So now let's actually look at a spectrum and see how it does fragment. Okay. So if we look at our spectrum down here, we want to find the different fragments and assign them. Okay. So this right here is our molecular ion peak right here. And we have a loss of, ooh, what's that loss of? It's a loss of 15 right here. So what fragment is associated with that loss of 15? And if we look at this right here, that would be the clipping off of that methyl group, right? So that loss of 15 is going to be a C fragment of some sort. Okay. So then we also see a 58. Ooh, we kind of predicted a 58, didn't we? Yeah, it was that fragment there. It's this fragment here. With some kind of fragmentation charge there. And we also predicted a 43, which is this right here. And it's actually could be this right here if we just lost a hydrogen. So it could be either one of those fragments. Or possibly both, because that would be fragmented from the same fragmentation. And that's actually because we have two sources of that approximate mass fragmentation. That's why it's actually becoming our base peak. We have a lot of fragments that can be created that way. And then if we go to our other fragmentation, that was just our McLafferty fragmentation pattern. We also have these two other fragments possible, and they are also in that 44 and 43 pattern right here. So we also have this as a possible fragment and this as a possible fragment right here. And they're both in the 44 to 43 range. Okay. So does the peaks we see make sense for the structure we have? Okay. Which fragmentation was the real fragmentation? Trick question. They're all perfectly valid fragmentations, and they are all present in our spectrum. We see the loss of the methyl group. We see the loss of the other group. We see what could be the loss in the McLafferty. Sorry. Okay, so you see how being able to think about all the different ways it can fragment and then assigning those fragments helps you build an idea that you can positively identify the fragments and the structure. All right, any questions on this one right here?
So if we had two different fragmentation patterns and one was significantly more likely, we would see a larger abundance of those fragments, correct?
Correct. And so let's say you had something that was producing a lot of the carbonyl fragment coming off. Your peak for that fragment would be higher. But that doesn't mean that the other peaks wouldn't exist. So they might be lower intensity, like these are here, but the idea that your highest fragment peak is your most prominent fragmentation pattern. And notice this one is high because we have 4 different fragments that can fit into that range. Did that answer your question?
Yes, thank you.
Good. Okay. So let's move on to the next one here. So I think we're only going to have 2 fragments from this because I think it's going to split some particular way. So this is one of those things that is kind of like rule 3, which is the more branching you have, the more it's going to fragment. And then that kind of small molecule clipping. So what I think is going to happen is that I don't think we're going to clip here because that is going to give us, 2 primary radicals. So I think the major fragmentation is actually going to be the loss of bromine first. Our major fragmentation is going to be the loss of bromine right here. So that should give us a 79/81 peak as a fragment peak. And it should give us a C3H7, which is, if we look at our table here, nice and slyly here, that is a 43 peak. 43 peak. That's this group right here is 43, and this is 7981. Okay, so now let's go look at our materials, what we see in the end here. And we have our molecular ion peak, and our molecular ion peak is 122, 124, and they look about level. So that's a great indicator that we have bromine in there. And so that's the molecular ion peak, right here. So now let's figure out if, though we lose bromine from that 142, 122, 124 peak, what's the molecular weight of the remaining fragment? The molecular weight of the remaining fragment is 43. So this is our fragment of the C3H7 right here. But we should still see the bromine fragment. Do we see the bromine fragment in our spectrum here? And the answer is yes, we see right here. It's not very prominent. Maybe it lost the ions, the ionization went to the fragment and left the bromine more neutral or radical. But we still see that 7981 peak on there. So this is our bromine fragment. This is our other fragment, and this is our molecular ion peak. Okay. Questions on that one?
How does the charge have an effect on the relative abundance and the peak size?
It doesn't have a charge. It's not based on relative abundance. It's this, if it has to be ionized to be detected. So if it will lose the charge to the fragment and become like a radical, it will not be sensed or separated by the device. So in things that have stable radicals, you might not see them. Things that don't, or things that don't have a strong positive charge. Like a carbocation is a different strong positive charge. The bromine positive is not a very common ion, and therefore it's going to have a lower susceptibility, so we see it less. Okay? Because remember, in the molecular ion peak, we have ionized the entire molecule, and so the entire molecule has a positive charge. And so to have it fragment, sometimes the bromine will take a positive charge with it, but it's less likely than having the carbon take the positive charge with it. Okay. Okay, so now let's put a couple more rules together. Let's use the rule of 13 and then the fragmentation pattern to try to assign what we have. Okay, so, but before we do our rule of 13 with our molecular ion peak of 134, let's look at the spectrum and see what we might expect to see as far as what kind of structure we're expecting. Okay, just from looking at those three labeled peaks, what's the first thing that jumps out at you besides the molecular weight's 134? Anyone? Anyone? Bueller? Benzyl.
The 91
right.
peak.
All right, I got that in the group chat there. That's exactly right. We're expecting this tryptilium or this benzyl peak to show up here. So we're looking for a benzene ring at least. So let's go ahead and apply our rule of 13 and try to figure out how to get to our molecular formula and see if it supports our fragmentation. Okay, so let's look at 134 and let's go ahead and, come on, there we go. All right, let's do our rule of 13. 134 divided by 13 is equal to, well, that'd be 10, which would give us 13, which would give us 4 remainders. So C10 H10 plus the remainder of 4 gives us this as our starting material. Okay, C10H4. However, okay, we know we need a hydrogen deficiency of at least 4 because we have a benzene ring in the system. We have that benzylic ring, so we need at least a hydrogen deficiency of 4 because the 3 double bonds in benzene plus the ring. So we need to account for that. So let's go ahead and start taking away hydrogens to figure out where the rest of this goes here. So if we wanted benzene ring, that would be C6H6, okay? So how can we get rid of some of these hydrogens? So one way is, well, let's get rid of, let's see, we want to get rid of hydrogen. So how would we get rid of hydrogens? Anybody have an idea? What do we have a substitution for in that, in our rule of 13? Okay, so we can get rid of some carbon. If we got rid of 1 carbon and 2 hydrogens, that's equal to an oxygen. Okay, that doesn't get us very far. Okay, so where else can we go? Where else can we go? Well, let's lose a carbon. Well, no, let's lose some hydrogens here. Let's see, we want to lose at least a few hydrogens to get us our hydrogen deficient. Actually, let's calculate our hydrogen deficiency on this right here, as we have. So we have 10 minus, we don't have any halogens, we don't have any nitrogen. So what's the equation for hydrogen deficiency? Carbons minus 1/2 the hydrogens. So
Minus hydrogens, okay.
1/2.
And then minus 1/2 of the halogens, which we don't have.
Right.
And then plus 1/2 of the nitrogens, which we don't have.
Right.
Plus 1.
1. All right. So let's see, right now, just in this formula here, we have 10 minus 7 plus 1 is equal to, let's see, 10 minus 7 is 3 plus 1. Oh, look at that. We have a hydrogen deficiency of 4 already. So we have at least a benzene ring in the system. Okay, so that's great. Okay, so just our base system here lets us have a benzene ring. So let's start running with this and see if we can't figure out what else we have here. Okay, so do we have any other major fragments? Let's see, this 43 fragment. What do we think this 43 fragment might be? Let's see, if we look in our book, it's commonly a C3H6 or a C2H2O. I'm sorry, a C3 carbonyl compound or having a nitrogen in there. We don't have an odd molecular weight, so we don't have a nitrogen in there. Okay, so we can plausibly start with a benzene ring because we have that. And so we have 10 carbons, and so that takes away 6 of them, so we'll have a 4 carbon chain off here. So we can start there. Let's see how many hydrogens we have. We have 5 hydrogens, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hey, we have a plausible structure just using our rule of 13. Okay, so now let's see if this structure fits our spectrum. Okay, so I'm gonna go ahead and erase the rule of 13 stuff because we've already done that to give us our thing. I'm gonna rewrite the empirical formula to make sure we don't forget it. Okay, so our empirical formula is C10H14. Okay, so the benzene ring, the fragmentation right here would give us this fragment here, leaving us with 1, 2, 3, which is C3H7, which gives us a C3H7 is a 43. Great, okay. And the loss of mass between here is 43. Okay, so we started with the rule of 13. We got to an empirical formula. We saw if we had enough of a hydrogen deficiency to actually draw the spectrum out, and we have this. All right, I'm going to throw a wrench in this. When we ran this reaction, it had oxygen in it. So what do we do with the rule of 13 to help us assign where our oxygen might, number one, what our empirical formula would be, and number two, does it still fit our fragmentation pattern? Okay, so if we look at our rule of 13, we have oxygen has a molecular weight of 16, which means that is going to be substituted for 1 carbon at 12 and let's see, that's 4 hydrogens. Okay, so that gives us a total of 16. So let's turn our empirical formula into C9H10O. Okay, so if we had that as our empirical formula instead, let's see what we can do to fragment this up. Oh, you know what? If we just have, we don't want the oxygen here, probably, but it can be somewhere over here because that'll give us that allylic cleavage and still give us that benzyl group here. So without any additional information, all that we have is an oxygen here. The only thing we can say is that there's some oxygen that's not next to the benzene ring because we get our system here, okay? So we would have to go to an IR or an NMR to finish assigning this structure, okay? So that's one of the limitations of mass spec. It gets you a long way toward the structure supporting it, but at some point it cannot go any further. Okay, questions on that? All right, now we're gonna put everything together, okay? Okay, boom, that's all you're getting. Okay, so first step, rule of 13. So we have 114 divided by 13, maybe 8. Anybody have a guess there? It's got to go in at least that many times. Maybe 8. And if 8 times 13, 8 times 13 is equal to 104, 104, and that gives us a remainder of 10. All right, yeah, that gives us a remainder of 10. So that means we have a C8, H8 plus 10 is H18. All right, so we have a C8, H10, 18. Let's now calculate our hydrogen deficiency. We have no nitrogen, we have no halogen, so we don't have to worry about that. And so if we do that, we have 8 minus 1/2 of the 18 plus 1. And let's see what our hydrogen deficiency is. We have 8 minus 9 plus 1. So our hydrogen deficiency is 0. So that means we have a fully saturated system, okay? So we have no additional things there. Okay, so we have a fully saturated system. We have, let's see, and we have approximately 8 carbons and 18 hydrogens. So let's just draw out the most simple structure from there. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now, from what we know about rule 1 and the long chain, how likely is it this is our structure? Oh, it's 9? Oh. Okay.
Not likely.
So not likely, right, because it doesn't do the clipping all the way down at 14, 14, 14, 14. So that might not be the way we do it. So let's look at what kind of fragments we have, and maybe that'll give us an idea of where to go with this, okay? So if we look at this, we have 14 to 99. So that's a loss of 15. Okay. Major fragment at 15 is CH3. Interesting. The loss of 99, well, let's see what 99 is. What is 99? Let's go to the book. 99 is a C7H15 or a C6H11. C6H11. Oh, that has an oxygen on it. That's interesting. And then there's another fragment here where it has 2 oxygens on it. Interesting. Well, it can't be the C7H15 because that would give us that straight chain clipping as we go. So that's probably not that fragment. So the other 2 fragments have oxygen in them. Okay, well, can we do a substitution for an oxygen and see if that might work out for something? Let's see. If we substitute 1 carbon and 2 hydrogens for oxygen, we can see that we can get that fragment. So let's go from our C8H18 down to having just 1 oxygen in it. So we're going to do our substitution on here. All right. There we go. We're going to do our substitution on there and put 1 oxygen in there. So we got, well, actually, let's do that. And so that's a total of 1 carbon and 2 hydrogens to substitute for an oxygen. So that's C7H16O. Okay, so let's see. Is there a way to kind of rearrange our thing such that, well, gosh, it can't be a long chain again because it would be clipping off the way we know. Let's look at this 43 peak again. What's 43? It's a C3H7 or, a CH3O fragment. That's a 43. That's interesting. Why is that interesting? Well, because we have a loss of 15 here, which would be the cleavage here. Then we have a major peak at 44, which would be a clip here. We might have a methyl ketone in this system. Okay, but it can't be that long chain methyl ketone because we would have seen it clipping. So, it's a very clean spectrum. So maybe we have symmetry in here somewhere. Okay, so let's substitute another oxygen in that system and see where we might be to see if we can't get more support for this fragment here, this 43 fragment. If we substitute 1 more oxygen in here, we're going to get C6H14O2. Okay, so that's giving us something kind of interesting now. Okay. So let's figure out a couple different ways to draw that so that we only get the fragment, this 43 fragment. So we want to go 6 carbons, we need 2 oxygens, but it needs to create a fragment that looks like that and a fragment that looks like that. So that would be there. We don't see a loss of 17. Now, why am I looking for a loss of 17? 1 carbon plus, oh, you're right, it is, okay. So this should be 14, which makes this 12. Is that what you're saying in the, is that right? So, okay, so that still takes us there. Let's see, so we still have C6, 1, 2, 3, 4, 5, 6. We have a nice clean spectrum. We don't have a loss of 17, okay? Why do I ask about that? If we had a loss of 17, or if we had a loss of 18, we would be looking for an alcohol, and because water is a small molecule that goes off, right? So we don't have an alcohol here. So, but we have a symmetrical system here. What if we had another carbonyl there? So let's redraw that as all right. Now let's look at the clipping, how the clipping would go. Okay. So let's say we clipped here. That would give us 15, and this side of the fragment would be 99. Okay. Okay. Cool. If we clipped here, this fragment would be 43, and this fragment would be 43 plus 14. So, we actually see that right here. And if this clipped here, that would give us a 43 plus 14. And if this clipped here, that would give us the 99 and the 15 loss. So I think that maybe we have this symmetrical diketone compound. And thank you for the correction. I messed up on that. Now, is that meet our empirical formula? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 2 oxygens. So is my math wrong again? Oh, so this was, it's a 4 substitution, so this is 10. And this was 14. Yeah. So our empirical formula is correct if we substitute 2 oxygens, and the structure matches that, and the fragmentation of that structure matches. Okay. Yeah, this is a hard one. Don't worry, we're going to go through a couple more of these. But a lot of times, for example, on a question set, you're going to have to do it like draw something and see if what you drew matches the fragmentation pattern. And if it doesn't, you do a substitution. And then you see if it matches your fragmentation pattern. And if it doesn't, you do another substitution. And so it's not always, rush to the final answer here, but I believe that this structure here matches our fragmentation pattern and matches our loss pattern just fine. Okay, questions on that? Okay. So I believe that's the last of these questions I had for us today, okay? Any questions or other, have you been reading ahead and you were looking at other weird fragmentation patterns that you might see? In the slides that I have posted, at the end of the slides here, there's a set of common fragments we see based on the functional groups, okay? So I just wanted to kind of draw attention to certain fragments of these because they're not 100%, but certain things you want to look for. Like I said before, does it have an alcohol in it? We're looking for a loss of 17, or we're looking for a loss of 18. Okay. So let's just hit a couple extra. Where is it? There we go. Just by functional group and look for common ways that functional groups break apart. So this is, all right. Sorry, I'm just trying to, okay. So again, long chain alkanes, you're gonna look for this clip, 14, 14, 14, 14, 14. That's what you should see in all these. And again, it's a high molecular weight, so the molecular entity is not very big. However, if you have even one branch here, that secondary carbocation is favored to clip. And so we're going to see that as it's going to clip here first, meaning that most of the upper fragments will not be present. We're going to see those smaller fragments based on where we've clipped it off. And so what we see is that this is a major peak at 57. And then the other side, or after clipping there, is the 85, which we see here. So if you know all you have is carbon and hydrogen and it's a saturated system, look for that pattern. Okay, let's see, we get out at 12:30. Yeah, okay. So I have a couple more. Already talked about rings. Already talked about the allylic clipping. Aromatic rings, even when you have multi rings like this, you're going to see a large molecular ion peak. So this is a bigger than benzene right here. And notice that we don't see, if it was benzene or something that was benzylic, we were looking for a 77 peak for benzene and a 91 peak for that benzylic peak. This has neither one of those. So you're starting to think, oh, it's aromatic because the huge ring, the huge molecular ion peak. However, it's not a simple benzene. It must be something that's fused. So that's another subtle thing that you can see by looking for fragments you know and love. Okay. Okay. So this is an idea of looking at different isotopes of alcohols and looking for different fragmentation patterns. So the first one is the straight chain. And so we see not only that straight chain, clip, 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 but also the loss of water as a major fragment. The first fragment is the loss of water right here. And then there's also another loss, which could be a CH3 and water, and then another loss right here. So we'll see that, look for that OH peak. And again, once we get into adding IR to this, you'll be able to see whether it's an alcohol or a carbonyl compound just by looking at the IR and give you additional information about the system. Okay, once you have your alcohol on a secondary carbon, you're gonna again see the loss of water, but you're gonna see that allylic cleavage, that cleavage near the thing giving you your major fragments. And that's why this is your major fragment, not these stepped, ones. And again, once you have a tertiary alcohol, that is going to be your number one fragment, almost always your parent ion peak as well, which gives you this large peak. So that's what to look for with alcohols in particular. So in this one, we're looking for a couple different things. We have a benzene ring, but we also have an alcohol. So we're looking for a loss of water somewhere, a loss of 18 somewhere. And we're also, because we have that alkyl group there, we're looking for a peak in 91, but we're also looking for a peak of just benzene by itself. And so we actually see the benzene by itself and the benzylic peak is greatly diminished, okay? This only happens in phenols, by the way. It wants to clip off that ring and stabilize that phenolic ion, and then it will, so this is kind of an indicator that you might have an OH on your benzene ring if you don't have a strong benzylic peak and you know you have a substitution. And ethers undergo that, the allylic cleavage. So you'll see fragments come off that are similar to the small alcohol peaks. Aromatic ethers always clip off the aliphatic group by themselves, leaving us a stable oxygenated benzene ring. Okay. So that's actually kind of an interesting one. You'll always see that kind of clipping off of this first as a major fragment to give you this, and notice that's here. But then you can also lose the fragment itself, giving you a benzene peak as well. Notice that's not the 77 peak we were expecting it to have. It's the 78 peak because it has to go through that rearrangement. Okay. And then, yeah, ketones, we're looking for CO losses, anything with a heteroatom, like Lafferty, and there, that's the last one I want to talk about. Straight chain carboxylic acids. Straight chain carboxylic acids are actually one of the few things that actually breaks that rule about the larger molecular weights not having a strong molecular ion peak. Okay, and one of the weird things about it is the fact that that carboxylic acid can stabilize charge. It actually does allow it to have a significant molecular ion peak, even at high molecular weights. It's probably the only one that breaks that rule. That the higher molecular weight you get, the more likely it is to not have a molecular ion peak, except for carboxylic acids, especially straight chain carboxylic acids. Okay, all right, we're getting pretty close. Any questions to finish up today? If you go to the book, there are a bunch of these that we'll be using in our exercise, looking for specific patterns of breaking up stuff. Okay, question?
Can you hear me?
Yeah.
Yeah, in phenol spectra, can we see M-1 peak?
M-1 peak. Let's see. We should see an M+1 peak because, let's see.
Right.
No, we just see the M molecular ion peak.
Like in alcohol, we can see M-1, but in phenol, it's not like, it will not be appear.
Right, and the actual, it's interesting because the hydrogen on the phenol is more acidic than the ones for here.
Yes.
So, but it is stabilized to the point where you actually do see it. This is this is the electron impact. They're all electron impacts. So. All right, good catch. I forgot that. Okay, well, I will go ahead and stop recording and stop sharing. Then let's see, stop sharing is up here.
I had a quick question as well.
Oh, okay.